Okay, so this is just going to be a really super rough, description of Buckingham's pi theorem. And, just, again, super rough, not very mathematical. Just give you a basic idea behind the concept and go from there. So one thing just to note, Buckingham pi theorem is extremely vital in dimensional analysis. And dimensional analysis is super important for, people that are doing experimentations, creating formulas, and just going about life in that regard. Also creating, physics rules. So if you do physics, this is actually going to be very applicable to you, particularly as you progress onwards, particularly when you're like, hey, how exactly did they reach the idea that rule, that law that we created, like, Newton's and all those worked? And behind the scenes, dimension has played a role in that. So just keep that in mind, particularly if you go on into those, fields, and look at applying dimensional analysis in that regard. So it's not like this murky water kind of a situation. Now, the whole idea behind Buckingham pi's theorem is just a formalization of Rayleigh's method. So you would have seen Rayleigh's method at some point. And it's just a formalization of that. So Rayleigh's is more like a conceptual kind of idea kind of thing. And Buckingham pi's just steps it up in the, the mathematical side. And the idea behind both of them is that when you have rules, natural laws or physics laws or physical laws, the units of measurement that you utilize should not matter in the, overall arcing rule. So the units of measurement, and the units of measurement we're talking about, like if you use metric or imperial, etc., is not going to make a huge difference. Again, think back to those physics laws that even from high school. You would basically just be able to tweak it to fit whatever units of measurement that you are using. Right, so the idea is that this should not matter. And that's where the overall idea behind the dimensionless products is going to come from. It's going to be a way to make sure that this is going to work out. Okay, so that's like the fundamental aspect of it. Now, to describe what is going to happen, I'm going to do something not entirely fully mathematically correct. I just want you to visualize it, kind of a situation. So think about the idea when you have a function of x and y, but you know that y could be a function of x, okay? Which means you could rewrite this function and in terms of x and say this was actually like x minus 3 kind of situation. So it's utilizing that kind of idea where you have some variables in a function, so it's a function with these variables where it's dependent on these variables, but in this situation you kind of can rewrite one of those variables it's dependent on in terms of the other, and then you can rewrite the function. So it's kind of going to use that. It's not going to use it directly in this situation where you could have actually, and this is important, so you could rewrite that like that and say like that kind of a situation, and then you could actually rewrite this function here as just x equal to the 0. In other words, wherever your y was, you could have replaced it by x minus 3, so it would technically look like a new function, and that new function would fulfill the overall duty of everything kind of situation. And that's what Buckingham pi's theorem basically does. So kind of what it does, again, this is not mathematically overall archingly correct kind of a situation, it's just so that you can visualize what is going on here. So what Buckingham pi's basically says, it says, yes, you have this function and you have a bunch of variables. Okay, so you have n of them equal to 0. Then it says, listen, we can write, we can clump up our variables into a new term, and we're going to refer to these terms as pi products. So you could have like pi 1 is going to be a function of some of these variables, not necessarily all of them, and pi 2 is going to be a function of, again, some of these variables, not the same variables as pi 1 necessarily. There will be differences occurring, and then you're going to have like pi 3, etc. It's just going to be a function of some of these variables. But what you're going to do here is, now because you have the situation, you can rewrite this original function, just like we did here. So we have a new function in terms of these dimensionless products. So the dimensionless products part is slightly new. So you will make sure that whenever you create these, their dimensions are 0 kind of a situation. So they are dimensionless. So when you create these functions, they're dimensionless. Here, you didn't really care. So, but the idea here, they are going to be 0. So that's where that comes from. So you have a bunch of variables. You're kind of going to reduce the number of variables you have by clumping some of those variables up and creating terms. And you're going to create them in such a way that all of these are technically going to be, and again, each of those variables are going to be dimensionless. And if you can do that, that means that, when you work out everything, it's not going to depend on the units of measurement. Because all those parameters are dimensionless, those units of measurements, the factors involved in them are going to kind of cancel out. So you know that, it's going to work regardless. And that's the main idea behind Buckingham Pi's theorem and Rayleigh's method and everything like that. Now, there is another aspect to this where we can actually tell you exactly how many dimensionless products you need. And that comes from the fact that P is equal to N minus K, where N is the number of variables you have, and K is the number of dimensions you use. Now, I wouldn't overall stress about finding out or figuring out why this works the way it does. It comes from linear algebra and the rank and nullity and basis vectors. When you hit linear algebra, you'll be able, to understand where this is coming from and why it works. But it has to do with linear independence and the basis vectors. So when you hit there, think about this theorem again, and it'll become a little bit clearer to you.